Right, so the last talk is from for this session.
Wait,
by
it's
Marino
plugged.
Mikulan, who's now going to connect the computer to the projector. And it's on bigraphical models for container-based systems. We should add that Marino is probably one of the few people in the world who understand the bigraph model. So
Well, maybe not. Hopefully not. Okay. Okay, thank you very much. So, yes, this is a talk about formal methods, basically, for containers and microservices. And so I don't think I needed to explain how much beautiful are microservices to this audience, since we are talking about this for 2 days by now. And you know that by now containers are emerging as the leading way for implementing microservices, because they naturally support separation of execution as intended in microservices, the special tasks in the development of microservices and so on, portability. They're much lighter than usual virtual machines, and they have a notion of composition, which I want to explain better in the next slide. In fact, the containers are made to be composed, are intended to be composed. In which sense? We can identify two kinds of compositions. The first one is what I call horizontal composition, where containers are put on a par, on the same level, and connected by some channels, some networks, something which allows to exchange messages. And on this kind of communication, I intend also shared volumes, like in this case. This is a channel which allows two containers to communicate. And then there is another kind of composition, the vertical one, where you can put components inside containers, like code, like specific libraries, which are taken inside a container to complete its behavior. And this composition can be made by developers or by deployment, and by means of suitable tools. I don't know if how much standard is this nomenclature. I call them horizontal and vertical for my mathematical background, because there is a clear mathematical motivation for these names. But I hope they are understandable. And the composition here is, in this case, is defined by means of, well, for instance, Docker compose configuration file. This is a usual YAML file for defining 3 containers, which are connected by 2 networks, front and back, for instance. And we define the images, the containers, the various components, and so on and so forth. So a Docker compose YAML file defines the structure, how containers are composed. Then this configuration is fed to an orchestration tool like Docker Compose, yeah, exactly, which creates all the containers, the networks, the connection, and so on and so forth, and launches the system. Okay, that's fine. Now, there is a question. How we check that the composition is correct? What do I mean? It is easy to misconfigure a configuration, especially of a large system, when you have hundreds of containers. And by misconfigure, I mean, for instance, a container might request an access to a service which is missing, or which is not connected to a network. It might happen that you define a link to a container which is not connected to a network to your container. And this may raise maybe a runtime error, because you're just trying to access something which is not allowed, available. Or there are some ambiguous declaration services. You just find the correct one. You finally find connected to a service which is not the intended one. Or maybe there are security violations. For instance, you may have a shared volume between 2 containers, and this allows to leak data from one containers to the other ones, to others, beyond the intended behavior of the whole system. And this is not only a static property, this is also a dynamic property, because a reconfiguration of the system during runtime may break properties, security properties which are held at the beginning. And in fact, actual composition tools are checking very few details about this, basically nothing. So you're alone, and the user strategy for dealing with these issues is by try and error, basically. You just try, check the system, configure the system, try, test it. If it works, you put it you deploy it in production. After a week, it comes out an error, then you fix it and try again, and so on and so forth, which is long, expensive, dangerous. So this is a perfect situation for applying some formal methods. We need some tools for analyzing, for verifying, possibly manipulating configurations, compositions of containers, even at runtime. For defining these tools, in first place, we need some formal models of what we intend with is a composition, what is a container, what is a service composition. So what is it? What should be this model? Well, it must support some logical connection of components, horizontal and vertical composition that is nesting, as we intended before. Must support dynamic reconfiguration, different granularities of services. It must be flexible and open. I mean, it should be easy to extend to add new features to this model, as long as we discover new needs, and many other aspects. So I look at this, we said, oh, wait, I saw this before. The solution was, well, there was the bigraphs. Bigraphs was well, by now old model, introduced by Robin Minner almost more than 15 years ago, as a general meta model, actually meta model for distributed communicating systems, supporting composition and nesting. That was precisely the slogan by Minner. And so we started working on this, trying to apply bigraphs to containers, and we came out with this proposal. I will not give it the formal definition. There is a formal definition, mathematical definition, what is a local directed bigraph. I'll give you some pictures, but in the paper there is a formal definition. So what is basically a local directed bigraph? It is a kind of graph like this, with nodes. Nodes are these basically stuffs. Everything you say beside arrows are nodes. Each node is given a type, specifying arities, that is the kind of connections, polarities. The arrows are directed. Can be nested, it is important. Nodes can be one inside the other. So basically they are connected, but also nested, like in a tree. And there may have sites, that is holes, which can be filled with other stuff, other bigraphs. And the arcs, these connections, can connect nodes to nodes and to names, to interfaces. There is an external interface and an internal interface. These are precisely the names of the interfaces given by Minner in 2003. This is not nothing new. It is not specific for containers or components. And okay, and that's it. Then the meaning of the arcs is access. So if a component, if a process wants to access some resources, then I draw an arrow from that component to the resource. Okay, that's the reading. And in fact, each container can be represented as a local directed bigraph, this kind of bigraph. So the interface contains the name of the container, the ports which are exposed to the side, the required volumes and networks and so on. Every data you need to in the external interface of the container. The container may have holes, maybe needed to fill with some further data. In that case, there may be sites of an internal interface, which is where I can plug something inside the container. And an important remark: this is simply just a picture. This is not a picture. This is a graphic representation of a mathematical object, which has a precise definition. This is formally an arrow in a category. In the sense of category theory, defined by the structure of the terms. So it is just a graphical representation, which is a nice thing. We can draw the picture to represent graphic mathematical objects. And also this container, this is the processes, and the nets, for instance, the nets which are required by the containers, the volumes. And being arrows, bigraphs can be composed. The composition is defined in a mathematical way, and it turns out, quite surprising maybe, that the composition that is implemented by the Docker Compose corresponds precisely to the composition in the category of the bigraphs. So the mathematical model captures precisely the notion of compositions as we intend in composing the model. For instance, in this example, we can see that three components, which are, well, components we defined before with the front and back networks and so on, which are plugged inside an environment, a context bigraph, let's call it a deploy bigraph, which corresponds precisely to the Docker Compose YAML configuration file. By precise, I mean there is an automatic tool, an algorithm for translating the YAML file into that bigraph. This is algorithmic. And after translating this, we compose according to the rules of composition of bigraphs, you get the composed system. Which means basically putting the stuff together inside the holes and connecting the arrows as you expect. Okay? So this seems to be good news, because it means that the model we have built seems to capture an important aspect, the vertical and the horizontal compositions of bigraphs, of containers. And so what can we do with this model? For instance, we can just use the graphical representation now of containers to analyze the structure, analyze the systems using techniques and tools from graph theory. No? Simple example, valid links, the issue as I told you before. I want to guarantee that if a container has a link to another one, then the two containers must be connected by at least one network. This can be translated formally as a condition on the resulting graph. Corresponds to simple conditions. Say, okay, if there is that conditions, then there must be also a network. This connection to links, then there must be also a network. It is easy to check this fact on the graph, on the resulting graph. It's just a matter of looking to the connections. A more interesting example, safe network separation. So assume that the networks or volumes, the same, have assigned different security levels, hierarchy of security levels, like in Bell LaPadula models, for instance. And for instance, that admin must be more secure than guest networks, which must be more secure than public networks. Okay. And I want to guarantee this property, that the data from the higher security network cannot leak into a lower security one, even going through different containers. How can we enforce this property? When we have 100 containers and 50 networks and 40 shared volumes. Mm. Actually, this can be reduced to a simple reachability problem inside the graph representing the system. So you can translate the statement in this one. For each pair of nets Mn such that M is greater than N as a hierarchy, there is no directed path from N to M. That is, there is no way that the lower network can reach the higher network, going through different paths. And in this case, for instance, it's easy to see that in this example, it doesn't hold, because if the front is getting back, for instance, then we can go through from back to front, going through this middle container. But even if we drop, for instance, the middle container, there is a path, isn't it? Because we can go through the shared data volume, which is shared between the front and back. Okay. So everything, all this stuff has been implemented in a tool, which is called a prototype tool, Docker2LDB. It is very simple. It's just a prototype. It's written in Java using the JLib library, whose main architecture is over there. It's Marco, when he was in Udine. And it takes a Docker Compose configuration file, a YAML file, builds all the objects, and checks for validity for all this stuff. So, for instance, this is the kind of output we can obtain, for the analysis of the security levels. Okay, so let's go to some conclusions. So I'm not too late. So what we've done, we're proposing a formal model based on bigraphs for systems based on containers. And this model captures correctly the notion of horizontal and vertical compositions, processes and containers. Can be applied for static analysis, as we've seen in the examples, and there is a simple prototype checker. And there's a lot of things to do that can be done on this model. There are many other static properties that we can consider beyond those related to composition. And in particular, it would be interesting to consider the dynamic properties. What do you mean by dynamic in this case? We mean change the configurations. The system, the whole system can be modified by replacing containers or parts of containers with others. And this is very easy to represent in bigraphs by means of graph rewriting rules. Graph rewriting rules like we've seen in many other situations. There is the old theory is over there, is ready to be applied. But in this case, you can represent, for instance, a notion of updating of a container that is replacing one module with another one just by a simple graph rewriting rule, which takes a module and replaces it with a new one. And adding this dimension, we can represent horizontal scalability, for instance, replicating of containers to scale with the load, container replacement, and so on. And with this dynamic aspect, we can talk about properties which must be ensured even after configuration of the system at runtime. So we can check temporal properties. Okay, so that's is what I want to say. Okay.
All right, thank you for a nice talk. Marino, my question is, always I like when there is some kind of formalization or some practical approach in computer science in general. Always it's nice to have underpinning so you can do some analysis, which sometimes humans are not able to analyze. And the example that you gave is quite nice, actually, the security and legal information or passive information. It's quite nice because even practitioners sometimes don't know where the information goes through, right? Now, this is very fine, but in the context of microservices, all right, so one of the purposes of microservices is just to produce this containers, let's say, very quickly, right? Change code, deploy, needs, deploy. Now, this is a lot of learning there, right? And
Mhm.
the timing for concepts until deployment increases incredibly, right? So, how you fit the theory that you're trying to push into the practice or the efficiency of microservices?
Okay, the first, the main context where we imagine to apply this theory is at the level of deployment, first of all. So it is when you decide to deploy the containers and to plug them together and to check that everything was as intended. This is the very first intended situation. So it is when you want to go in production, for instance, and testing before that. But of course, it can be extended also on the side of the development, because you can, in theory, work also inside the container to check that the connections are the right ones. Basically, any topological property, in the sense that the connection between components and processes inside containers and from containers to other containers can be checked. And I think this is a kind of property which is transversal for both from the developer and the deployer. So, is this an answer to the question?
My question was in terms of time frame.
Ah, the time frame.
Time frame, because we need sources to be in order to understand and apply your theory.
Mm.
And on the other side, you've got microservices, which is
Well,
a day or a couple of hours.
well, and basically, if yeah, but basically, the aim is to give the developer and the deployer a tool to use it. And they don't need to understand what are bigraphs. Okay, this is just a drawing. This is stuff for us.
Other questions? Yes.
Thanks for the talk. All these things reminds me a bit of service composition, and there are also different approaches that have been used. So one question, are all the securities properties that you are checking polynomial, or do you think, are you thinking also of security properties that are more than polynomial to check? And do you see also this analogy with service composition, and probably also thinking to have your model or bigraphs to, for instance, to ask or to fill the gaps with new services or new containers that are not there, to check if a solution is feasible or not?
So I will answer the second question first. At the level of abstraction of bigraphs, yes, you can apply them also for service composition, basically, because or for components composition. Just the readapting. The model is very flexible. You can adapt it also to other contexts. In this case, we focused on containers, and we defined the signature that we say that is the type of nodes needed for dealing with containers. But you can easily adapt it to other situations. Coming to the first question about the complexity, as you said, for the properties. It depends on the property. And we said it seems that it depends is the mantra of the of the talk of the conference. The model is a graphic model in the end, and then the property you can prove on them on this model are those which are usually in graph theory. You know, in graph theory there are easy problems and very hard problems and impossible problems. It may be that your property comes out to be impossible to decide, which is already a result. Maybe you can understand that, okay, I'm trying to face a hard problem, a very difficult problem, or a simple problem, for which there is maybe some easy algorithm. Having a formal model, a graph model for representing your structure, your system, is the first step to understand which is the solution.
The question was asked if this could be user unfriendly previously or hard to use by practitioners, but when I saw these pictures I was wondering, have you considered maybe inverting this process, so mapping the graph and generate the compose file.
Yeah.
So only valid manipulations to the graphic model could be actually made by a user.
Yes, this is a good observation, and I mentioned it maybe before in. No, they didn't mention, actually. Yeah, this is one of the applications. For instance, using the model for manipulating the composition. That is, for instance, you can read the YAML file, build a graph model, apply some optimization, some analysis, discovering that maybe there is a better configuration for the same services. Something can be moved around. Then you come out with a new bar graph representing the new system, and then you can print out the new configuration. Yes, this is one good application.
I have a question and a comment. Well, the comment is that I find that this matching between the bigraph model and the container deployment. I mean, it's a very nice matching. I find it very pleasant that bigraphs are.
I will talk about you the similar correspondence between bigraphs and Jolie programs.
Absolutely.
Next time.
But I think that is actually connected to the last comment. This allows for a lot of bidirectional transformations between the graphs and, for example, deployment plans, right?
Yes.
And I was thinking about your dynamic reconfigurations. Do you think it would make sense that instead of having people use, I don't know, Java libraries for infrastructure as code to modify the deployment of a system, to instead give them a library that is based essentially on graph rewriting rules? I think it might end up that it's even more readable than what we have now.
That's a good idea, a good proposal, in fact. I'm not an expert of human-computer interfaces, so maybe there is a better way to represent this stuff. And the user tell me that graph-oriented models are easy to understand. I'm not sure of this, but if it is true, no, maybe this is a good option for representing to the deployments. To see that means the state of the system to show, okay, there are connections. Try to configure the system. Click over this container, which is a bar graph, but don't tell them, and duplicate it, and then it spawns another one. Marco.
Last question, and then we go for lunch.
Thanks. So one of the, perhaps the main selling points of bigraphs, when Miller introduced those, were IPOs. So the ability to synthesize a minimal or optimal context that enable a certain computation. Do you have plan or ideas on how to exploit these in your model?
I haven't thought about this. And I think, let me think about this. Well, actually, you should, you could answer better than me to this, I know, but yeah, this could, okay, I'll tell you what is the story behind this question. The theory of bigraphs is extremely rich and powerful. It allows to derive so-called completing context for enabling transitions. If you are familiar with the borrowed context from graph grammars, it is a similar concept. And so maybe if you may have a system, you want the system to perform some transaction, some operation, you need something to add inside. Well, bigraphs allow to calculate the minimal context to add in order to allow this transition. A minimal family. And this is very powerful because you need, okay, how can synthesize the right environment for making this working? Okay, and I haven't thought about this actually, but I think it could be a very nice application.
All right, let's thank the speaker again.
Okay.